Good day. We will now be discussing a supplementary lesson on how we are able to actually calculate certain types of internal noise. Specifically, we'll be discussing first about the computation of thermal noise voltage or thermal noise power. Afterwards, we'll now go into the discussion of computing for shot noise current. And finally, we'll be looking into one of the most important aspects in the computation of noise signals, which is the signal to noise ratio. Now, with thermal noise, as mentioned a while ago, we can either get what we call its thermal noise voltage or noise power or thermal noise power. For noise voltage, it is equal to the square root of 4 kTBR, K being Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. The temperature, you have to make sure that the given temperature is in Kelvin. So the direct way to convert Celsius to Kelvin is by adding 273. The bandwidth of the signal in hertz, and the resistance of the resistor or the resistance of the circuit in ohms. For noise power, you only need the Boltzmann's constant, the temperature, and the bandwidth. So let's take a look with a few examples on how we're able to calculate thermal noise. So let's try solving a few examples with a bit of variation, and we'll try to look into solving both the noise voltage and noise power for thermal noise. So for the first problem, we are given a temperature of 300 degree Kelvin. The signal has a bandwidth of 10 kilohertz. And the circuit itself has a resistance of 100 kilo ohms. If we're going to determine noise voltage, we just have to follow the formula here, which is Vn, which is equal to the square root of 4 multiplied by K. K is 1.38 times 10 to the negative 23. Don't need to put in the units, as we just need a unit for our final answer. Then the bandwidth, which is 10 kilohertz. Well, I have to put the kilohertz here as it has a prefix. Putting in just 10 would make our solution and the answer incorrect. And a resistance of 100 kilo ohms. So this is 4 kT. Oh, I forgot the temperature. So let's just squeeze in the temperature here. Although, so it is 300 Kelvin. So 4 kTb and R is 100 kilo ohms. 100 kilo ohms. So square root. Let's determine the answer. So if you have your own calculator, kindly compute for the following voltages. So we will be having 4 multiplied by 1.38 exponent negative 23 times 10 exponent 3 or 4 kilohertz times 300 for Kelvin. This is not kilo, okay? We might be confused, but this is actually Kelvin. Multiplied by 100 exponent 3 kilo ohms. So I'm going to multiply all of these together, and I'll be getting 1.656 times 10 to the negative 11. And then I have to do a square root first, because I actually multiplied everything inside together. So now the square root would be square root of the answer. We have 4.06 something. Just click ENG once, although we don't have to, but because this is already -6. And we round off 2 decimal places, 4.07. Let's just move this a bit here. So our answer is 4.07. By now, you should already have understood what to do with the -6. So this -6 is micro, okay? And because this is voltage, the unit is in volts. So our answer for noise voltage is 4.07 microvolts. Okay? How about for noise power? So noise power is actually easier to calculate as it only requires K, T, and B. So that would be our 1.38 times 10 to the -23 multiplied by 10 kilohertz and our 300 Kelvin temperature. So the only thing that's missing would be the 4, the constant 4, the resistance, and the square root. So we have that already. Okay. So this is complete. This is K, temperature, and the bandwidth. Let's try to calculate that. So again, we have 1.38 exponent -23 multiplied by 10 kilohertz. So that would be exponent 3 multiplied by 300, which gives us 4.14 times 10 to the -17. Press ENG. So that would be around 41.4. Now, as we do not have the prefix for -18, we'll just write it as S. So, and because this is power, we put in watts. Again, the reason we did not convert this into prefix, as our discussion for the table only has us up until -12 or -15. Although I think there is a prefix for -18, but for simplicity's sake, let us just leave it as is. Just don't forget that for voltage or noise voltage, it should be in volts. For noise power, it should be in watts. Let's take a look at the second example. So the first thing that you'll notice is that our temperature is in Celsius. Our noise voltage computation, the temperature should be in Kelvin. As written here, Kelvin, or in order to convert Celsius to Kelvin, we just add 273 to the temperature, and then we'll have Kelvin. So before we go into the computation, we have to convert this into Kelvin by adding 273. And that would give us around 298 degrees Kelvin. Then that would be the temperature that we will be using in order to compute or calculate noise voltage and noise power. So let's do noise voltage again. So it's still 4 kTPR. So we have 4. The K, which is Boltzmann's constant, which is 1.38 times 10 to the -23. There you go. 4K, then a T, which is 298 Kelvin. Our bandwidth is 5.5 megahertz. 5.5 megahertz. Then our resistance is 500 ohms. Okay. And let's not forget our square root right here. So we have 4 multiplied by 1.38 exponent negative 23 multiplied by 298, our temperature. Then our bandwidth is 5.5 megahertz. So 5.5 mega is 6. So 5.5 times 10x 6 or exponent 6 multiplied by 500. Our answer. And then, of course, we have to do the square root. And it will be 6.73. As this is already negative 6, no need to press ENG. Although if press ENG, it would still stay the same. So our answer would be 6.72. So 2 decimal places. Oh, 6.73 as the 2 as 3 and this has 5 on its right side. And negative 6 is micro. This is voltage, so this would be in volts. Next, let's compute for the noise power. So it will be 4, no, it's only KTB. So 1.38 times 10 to the negative 23 multiplied by the temperature, which is 298 Kelvin, multiplied by the bandwidth, which is 5.5 megahertz. So let's take a look. So 1.38 exponent negative 23 multiplied by 298 multiplied by 5.5 exponent 6. And the answer would be 2.26182. Press ENG, so you'll have 22.62. So 22.62. Negative 15 is femto. F. Femtowatts. Because this is noise power. So if it's above 15, like 18, 21, you just leave it as is. Just like example 1. But for 15, it is actually femto, which is letter F. Negative 12 is pico. Then we have nano, micro, and milli. All multiples of 3 on the negative scale. Next, we have example number 3. So in example number 3, the temperature is given in Fahrenheit. So we have to convert it first into Celsius, then into Kelvin. So how do we convert Fahrenheit into Celsius? So as shown below, we subtract 32 first from the temperature, then multiply it by 5, then divide it by 9. So let us convert this first before actually going into the computation. So we have 5 multiplied by 120 Fahrenheit minus 32 divided by 9. And that would be equal to, so we subtract first 120 minus 32. We have 88 multiplied by 5, which is this, divided by 9. So press SMT. So 48.88888. 48.8. So 48.89 rather. So let's write it down. I think we should add anyway. No, 48.89. Again, this is just in Celsius. And then if you want to convert it into Kelvin, we have to add 260 273. So that would give us plus 273, 321.89 degree Kelvin. Okay. So we have to be careful that our temperature is already in Kelvin. Do not rush the solution. I know you'll be able to solve this using our formula, but one of the common mistakes is forgetting to convert the temperature into its appropriate unit. So you must remember to check if the temperature is already in Kelvin. If it's not, you have to convert it first. Okay. Now, once our temperature is already in Kelvin, why is this still in Fahrenheit? Kelvin. There you go. It's time to use our computation. So we have Vn is equal to, let's not put this one at the top. So we have Vn. So it's always 4. And K, which is constant, 1.38 times 10 to the negative 23. So temperature is 321.89 in Kelvin. Okay. Now, next, we have T already, then we need the bandwidth, 300 kilohertz. And then the resistance, which is 370 ohms. So the square root of this. So this time around, let's use the calculator again. So 4 times 1.38 exponent negative 23, our Boltzmann's constant, our temperature of 321.89, our bandwidth of 300 kilohertz, 300 exponent 3. Finally, our resistance of 370 kilo ohms, 370 kilo ohms. Gives us 1.97 times 10 raised to negative 9. And then we go with the square root, the answer. Then, oops, not ENG. So 44.41 microvolts. So this would be 44.41 because it is times 10 to the negative 6. It's micro, and this is noise voltage. It's volts. Finally, we will now be able to compute our noise power. Oops, let's use the black instead. Not there. Noise power, just KTB. So 1.38 times 10 to negative 23. Temperature is 321.89. And then this is in 300 kilohertz. So let's have 1.38 exponent negative 23 multiplied by 321.89 multiplied by 300 exponent 3. Okay. So it's 1.33. It's already negative 15, multiple of 3, which is femto. So it's 1.33 femtowatts. There you go. Okay. So hopefully you understand how we're able to calculate thermal voltage or thermal noise voltage and thermal noise power. Now, we'll go to our next supplementary topic, which is about computing for the shot noise current. Let us now proceed to the second part of our discussion, which is about calculating shot noise. Unlike the thermal noise, where we are able to compute noise voltage and noise power, for shot noise, which is affected by DC biasing, we are actually able to calculate its noise current. The formula is actually quite simple. The shot noise current is actually equal to the square root of 2q IB. Q being the charge of an electron, which is 1.6 times 10 to the negative 19 coulomb. I being the direct current in amperes, and B being the bandwidth. So let's take a few look at our examples and see how we are able to apply the computations for shot noise. So let's say we have, for our first example, we have a current of 10 milliamperes and a bandwidth of around 10 kilohertz. For our second example, let's have a smaller current this time. Let's have around 50 microamperes, just smaller than milli, of course. A bandwidth of around, let's say 30 or 300 megahertz. So let's take a look at how we will be able to compute for the following noise current or shot noise current. So for the first one, so again, the noise current is equal to the square root of 2 multiplied by the charge of an electron, which is 1.6 times 10 to the negative 19. Well, at least now you know of around 3 constants used here. So we have Boltzmann's constant, the charge of an electron, and of course, the speed of light. The current, which is set at 10 milliamperes. And finally, the bandwidth of 10 kilohertz. Then we'll just get its square root. So using our calculator, let's try calculating this. So 2 multiplied by the charge of an electron, 1.6 exponent negative 19, exponent negative 19 multiplied by 10 milli, milli being negative 3, of course. Oops, I forgot to put in the multiplication. So 10 negative 19 times 10 milli multiplied by 10 kilohertz. There we go. So the answer is this. Of course, we haven't put in the square root yet. So the square root of this answer would now be 5.66 times 10 to the negative 9. Even if you press ENG, it's already in negative 9. That means this is already in engineering notation. So let's write that in. 5.66. Negative 9 is nano. And the unit for current is, of course, amperes or capital A. So that is our answer for the noise current. How about example number 2? So same, as there are quite no variations with this problem, unlike thermal noise that has some variations because of the temperature. We have to make sure it is always in Kelvin. So we have the square root of 2 multiplied by the charge of the electron, 1.6 times 10 to the negative 19 coulomb. Our current is 50 microamperes. And then finally, we have the 300 megahertz. So mega. Hopefully you still remember our engineering notation prefixes, as that would be quite useful all throughout our discussions. Calculator ready? So 2 multiplied by 1.6, 1.6 exponent negative 19, so times 10 raised to x, negative 19 times 50 micro, 50 exponent micro is of course negative 6, multiplied by 300 mega, 300 mega is positive 6, exponent positive 6, and then the answer is 4.8 times 10 to the negative 15. Again, don't forget that we still have to do the square root of the answer, which gives us 6.93. This is in negative 8, so we have to press ENG once, and we get 69.28 nanoamperes. So 69.28, 69.28 nanoamperes. And there we have it. Now, the next thing that we have to discuss, or the last thing that we have to discuss, is actually quite an important thing in communication systems. And that is getting what we call the signal to noise ratio, the noise figure, and the noise factor. As we have discussed already, it's not really the amount of noise that's the most important, but how the signal power is compared to the noise power. Is the signal power too large or quite large enough to overpower the noise? Then it's good to go. But if they're almost the same, then that would be a big problem. So let's take a look at how we are able to compute or calculate noise power, not noise power, but signal to noise ratio, noise factor, and noise figure. This would now be the last part of our discussion for today, and this would involve computing the signal to noise ratio, noise figure, and noise factor. As mentioned a while ago, the signal to noise ratio is the comparison between the signal power and the noise power. And it's as simple as dividing the signal voltage over the noise voltage, or the signal power over the noise power. It can be represented as the absolute value or the absolute unit, or it could be converted into decibels as well. As we have discussed decibels from our first supplementary video, that shouldn't be a problem anymore. But we'll still show a few more examples. So let's have two main examples for the signal to noise ratio. So let's say we have a signal voltage of around 30 volts. And then we have a noise voltage of around 10 millivolts. And we are to determine the signal to noise ratio. Let's have a second example in which we have a signal power of 150 watts and a noise power of around, let's say, 30 watts. So let's determine its signal to noise ratio in both absolute units and in decibels. So if we are to determine signal to noise ratio, SNR, we just directly divide our signal voltage, which is 30 volts, divided by our noise voltage of 10 millivolts. Let's have that. So we have the 30 volts divided by 10 milli. Be careful that you include the prefix as part of your calculation. Normally, if they have the same prefix, you can actually divide them directly, as mentioned in our first supplementary video. But because they have different prefix, the top one or the numerator having no prefix, the bottom one having a prefix, we have to include the prefix. And milli is, of course, -3. And then it would show up as 3,000. Now, if we are to represent this in decibels, as this is voltage, you can remember from our computation and representation of gain and losses in decibels. When we use voltage, we use the formula 20 logarithm. So we have to put in 20 logarithm of our 3,000 here. Don't forget that because these two are both voltages, we don't have a unit below. So the logarithm of our answer, which was 3,000, multiplied by 20, and we will get 69.54. This time around, it has a unit, which is in decibels. Let's now move on to our second example, in which this time around, we have signal power and noise power. So let's try to find it in absolute terms first. So the signal power is 150. And then the one at the bottom is 30 watts. So 150 divided by 30 would be 5. Now, if you want to represent this in decibels, as it usually is done, we have 10 logarithm of this one, which is 5. And by virtue of computation, so the logarithm of 5 is equals to this amount multiplied by 10. Oops, I made a mistake. Let's do that again. Logarithm of 5 multiplied by 10, 6.99 or almost 7. Of course, this is already in decibels. You still remember why I used 10 instead of 20? Correct. As we are actually looking at the signal to noise ratio in terms of power, we use 10 logarithm instead of 20 logarithm. Please be reminded that 20 logarithm is used only for ratios of current and voltage. If we are going to use it for the ratios of power, we use only 10 logarithm. So that is how you determine the signal to noise ratio of a system. Now, the signal to noise ratio of an electronic system actually varies in depending on its parts or by parts. Sometimes it would have a different signal to noise ratio at the input as compared to the output. Although we want our signal to noise ratio as high as possible due to some limitations of technology and the components in hand and other factors, signal to noise ratio will be different in the input and in the output. With that being said, we look at our noise figure. So the noise figure is actually the ratio of the signal to noise ratio of the input over the output. So although the signal to noise is already a ratio, so the noise figure is a ratio of a ratio. When we are using the signal to noise ratio in the input and output and determining the noise figure, be careful that we are supposed to use the signal to noise ratio in absolute units. We won't be using the one in decibels. So let's have two examples. For our first example, let's say we have a signal to noise ratio on the input of around 100 and a signal to noise ratio on the output of around 50. And for our second example, let's say we have a signal to noise ratio of the input, which is around 35, and a signal to noise ratio on the output, which is 80. So for the first example, the input signal to noise ratio is higher than the output. In the second example, the signal to noise ratio in the input is lower than the one at the output. So let's determine the noise figure. So NR is just the ratio of the SNR input, which is 100, divided by 50. And 100 divided by 50 would be equal to 2. For the second one, we have a signal to noise ratio in the input of 35 and a signal to noise ratio in the output, which is 80. In this case, we would be getting a signal to noise ratio, or a rather noise figure, of 0.4375. So around 0.44. So what would be the significance of the following? Well, normally the noise figure in the input over output, we want it to either remain constant or become higher. Remember that a higher signal to noise ratio means a better quality for the signal. So having a noise ratio or a noise figure of more than 1 is actually quite bad. That means the signal to noise ratio actually became worse from the input to the output. Having a noise figure in between 0 and 1 means that the signal to noise ratio actually improved from the input to the output. Okay, again, the noise figure, if it's higher than 1, means a degradation in signal to noise ratio. A noise figure in between 0 and 1 means an improvement in the signal to noise ratio in the input and the output. The noise factor, on the other hand, is actually directly calculated from our noise figure. So we just convert this into decibels. So NF would just be our noise figure multiplied by logarithm first and multiplied by 10. So 10 logarithm of 2. So let's have that on our calculator. So logarithm of 2 multiplied by 10 gives us 3.01 decibels. And for our second example, a noise factor is just 10 logarithm of our answer from our number 2 example, 0.44. So we should expect a negative decibels here. Oops, not this one. Where's that? There we go. So logarithm of 0.44 multiplied by 10, giving us negative 3.57 decibels. Okay? So this first part will be our noise figure, and this one will be our noise factor. So in noise factor, a negative decibel is actually better because it means that there's an improvement in the signal to noise ratio. So a positive noise figure, or noise factor rather, means that there's a degradation of the signal to noise ratio of the output compared to the input. I'll be giving a few exercises for you as the last part so that you'll be able to determine your understanding of today's supplementary discussion. So please try the following exercises in order to be able to determine your understanding of today's lecture. For the first one, we are to calculate the thermal noise voltage and power given the following. For number 2, you are being asked to compute the shot noise current given the DC current and signal bandwidth. For number 3, you are to determine the signal to noise ratio of the following in decibels. So the first one for letter A is in terms of voltage, and letter B is in terms of power. And the last number, you are to determine the noise factor and noise figure for the following. I made a mistake a while ago. So could you try going back to my discussion? I keep referring to the first one as noise figure and the second one as noise factor, but they're actually supposed to be in reverse. The reason why it is NR is because noise factor is also known as noise ratio. And the one in decibels is actually the one called as noise figure. So kindly have that corrected. So noise factor and noise ratio are one and the same, NR, that's the ratio of the input and the output. And converting it into decibels is the noise figure. Thank you very much for listening. Hopefully you gained something new with this discussion. And as always, if you have any questions, if you need to make any clarifications or correct any mistakes I made in the computation, kindly comment on the comment box below, or do a direct message or private message so that I'll be able to correct it as soon as possible. As always, thank you very much and have a great day.